Welcome to Revised Chemistry with Mr. B. In this video, I'm going to take you through the whole of the atomic structure topic. That's if you're studying for AQA Combined Science, also called Trilogy. If you study in separate science, or yours is one of the other exam boards, just check your revision guide to make sure there's no other extra little bits that you also need to know. The first part of this topic looks at atomic structure, which is what atoms themselves are made of. So if we take a look at this atom, we can see in the center we've got a nucleus, and that nucleus is made up of protons and neutrons. Around the outside of the atom, we've got electrons orbiting on electron shells. Now you need to know the charges of these particles. Protons are positively charged or +1. Electrons are negatively charged or -1. And neutrons have no charge, they're neutral. You also need to know the relative mass of these particles, and it's measured in AMU, which stands for atomic mass units. Now, the protons have a mass of 1 AMU. The neutrons also have a mass of 1 AMU, but the electrons are much smaller. They have a mass of 0.0005 AMU. And you need to remember all of this knowledge for your exam. On the last diagram, how did I know how many neutrons, protons and electrons to draw? Well, I worked it out using information from the periodic table. So in the case of lithium, it has two numbers, 7 and 3. The bigger number, 7, is known as the mass number, whereas the smaller number is known as the atomic number. And if I want to find out the number of electrons, I look at the atomic number, so I know that lithium has got 3 electrons. If I want to know the number of protons, again, I look at the atomic number. So lithium also has 3 protons. However, for the number of neutrons, I need to do the mass number, take away the atomic number. So what does the mass number actually tell us on its own? Well, the mass number tells us the number of protons and neutrons in the nucleus. Let's look at another example, phosphorus. If I want to work out the number of electrons, I look at the atomic number. So for phosphorus, it would have 15 electrons. Similarly, for the number of protons, I would also look at the atomic number. So it has 15 protons. And a common question on your GCSE exam is, why are atoms neutral overall? And that's because an atom always has equal numbers of positive protons and negative electrons. So in the case of phosphorus, it would have 15 positive protons, 15 negative electrons, and 15 plus and 15 minus cancel out. So overall, there's no charge. To work out the number of neutrons, I would have to do the mass number, take away the atomic number. So in the case of phosphorus, it would have 16 neutrons. If at any point during this video you feel like you need a little bit more help on some of the ideas, then head over to C1 playlist of my YouTube channel, and there's individual videos about each of these ideas with lots more examples. We're now going to take a look at the arrangement of electrons within an atom, also known as electronic structure. Now, when we're drawing electrons on these shells, we need to remember some basic rules, and that is the first shell nearest the nucleus, also called the lowest energy level, can hold up to 2 electrons. The second shell, or the second energy level, can hold up to 8 electrons. The third shell can hold up to 8, and the fourth shell can hold up to 18. And when we're drawing electrons on these shells, we will start at the inside and work our way out. So let's take a look at an example. Let's have a go at drawing the electronic structure of a boron atom. So from the periodic table, we can see that boron has the atomic number 5. That tells me I need to put 5 electrons somewhere. So we start off by drawing the nucleus. In that nucleus, we know that we've got protons and neutrons, but we're just concerned with the electrons for the time being. We draw the first shell nearest the nucleus. That can hold up to 2 electrons. So I'm going to place 2 electrons on there. That shell is now full, so I need to draw a second electron shell. And I'm going to put 3 electrons on that shell, so that altogether we've now got 5 electrons for the boron atom. Let's look at another example, oxygen. So oxygen has the atomic number 8, so it's got 8 electrons. So here's the nucleus of the oxygen atom. The first shell we can put up to 2 electrons. Now I'm going to draw them in crosses this time, just to show that you can draw electrons as dots like the previous example, or crosses. That first shell is now full with 2 electrons. So I need to start a second shell. The first 4 electrons we place separately, and then after that we're going to double up with the electrons. So far I've put 6 on, we need 8 altogether. So I'll put another 2 there. So we've got 1, 2, 3, 4, 5, 6, 7, 8 electrons altogether. Now, like I said before, if you need any help with this, head over to my C1 playlist and there's a whole video about how to draw electronic structures. We're now going to talk about how atoms can change into ions. So when a chemical reaction happens, atoms can lose electrons or gain electrons to get a full outer shell and be stable. When they do this, they turn into ions. So let's look at an example of a fluorine atom turning into a fluoride ion. First of all, we'll draw the fluorine atom. We know from the periodic table it's got an atomic number of 9, so it's got 9 electrons, which will be 2 on the first shell and 7 on the second shell. Now, to be stable, it needs a full outer shell, so it needs to gain 1 more electron. So I'll draw it again now. It's changed into an ion. Now it's gained that extra electron, which I've shown with the cross. And with ions, we also draw brackets around the ion. Now let's think about the charge on the atom and the ion. Now with the atom, it's got 9 positive protons in the nucleus, 9 negative electrons on the electron shells. So overall, 9 plus and 9 minus comes to 0 charge. And remember, that's true for all atoms. They've got equal numbers of positive protons and negative electrons. With the ion though, it's now got that extra electron. It's still got 9 positive protons in the nucleus, but now it's got 10 negative electrons. And 9 plus and 10 minus comes to 1 minus charge. And we show that minus charge at the top right of the brackets. And notice how we don't need to show the 1 if it's just a 1 minus. Now, if you found that tricky working out the charge of an ion, here's an easy way. When you open your exam paper, you turn straight to your periodic table and annotate it in this way. So group 1 elements all make 1 plus ions. Group 2 make 2 plus ions. Group 3 make 3 plus. Group 7 make 1 minus. Group 6 make 2 minus. Group 5 all make 3 minus ions. And the middle section, the transition metals, often make 2 plus unless you're told otherwise. So in the previous example, fluorine, we would find where fluorine is on the periodic table. It's in group 7, so we know it makes a 1 minus ion. Let's look at another example of a beryllium atom changing into a beryllium ion. Now in this case, instead of it gaining 6 more electrons, it will lose 2 electrons. It will always do whatever involves losing or gaining the least number of electrons. So it's better to lose 2 than try and gain 6. So when it's lost those 2 electrons, the ion will look like this. We can now see it's left with a full shell, and we draw the brackets around the ion. Now, if we're considering the charge, a beryllium atom has 4 positive protons in the nucleus, 4 negative electrons, so overall it's got no charge. The ion still has 4 positive protons, but it's now only got 2 negative electrons, and 4 plus and 2 minus comes to 2 positive charge, which we write at the top of the brackets. Once again, to use the easy way of finding out the charge on the beryllium ion, we can see where it is on the periodic table. It's in group 2, and we know they all make 2 plus ions. We're now going to take a look at what isotopes are. Isotopes are different forms of the same element. So here we've got 2 types of lithium atom. One's got a mass number of 6, one's got a mass number of 7. And I'm going to use these models to show what the atoms would be like, where the black ones are standing for the protons, the green ones are the neutrons, and the red ones are the electrons. So each form of lithium has 3 protons because the atomic number is 3. Similarly, they've each got 3 electrons because the atomic number is 3. However, when we look at the number of neutrons, 6 take away 3 is 3 neutrons for this atom, 7 take away 3 is 4 neutrons for this atom. So our definition of an isotope is it's a different form of the same element that's got the same number of protons but different numbers of neutrons. I'm now going to show you 3 things that students often get confused about, and that's elements, compounds and mixtures. Here's a chemical element. It's a piece of magnesium. All the chemical elements are found on the periodic table, and what makes it an element is it's made of only one type of atom. So if we could see the atoms, I'm showing them here with these models, all the atoms would be the same. So make sure you remember an element is made of only one type of atom. Here's a different element. These models are meant to represent oxygen atoms, and we can see it's an element because there's only one type of atom. All the models are red. Yes, the atoms are pairing up to form molecules, but we've still only got one type of atom, so it's a chemical element. Let's see what happens when we react a piece of magnesium with the oxygen in the air around us. I'm going to be careful not to look directly at this reaction because it gives off so much light that it could harm my eyes. And then in a minute or two, we'll have a look at what we've made. We started out with 2 different chemical elements, magnesium made of just magnesium atoms and oxygen made of just oxygen atoms. And when they reacted together, they made this white powder, magnesium oxide. And magnesium oxide is an example of a compound because it's made from magnesium atoms chemically joined to oxygen atoms. So the definition of a compound is when you've got 2 or more different types of atom chemically joined together. A mixture is when you've got 2 or more different types of atom that are not chemically joined together. So we've still got some magnesium and oxygen atoms, but because they're not chemically joined together, it actually means that mixtures are quite easy to separate. If I want to write a word equation for the reaction I've just showed you, I need to remember that the starting chemicals that we call the reactants go on the left-hand side of the arrow, whereas the products that are made go on the right-hand side of the arrow. So we started off with a piece of magnesium, it reacted with oxygen in the air, and those 2 combined together to make magnesium oxide. The symbol equation for this reaction would be Mg for magnesium, oxygen is O2, and magnesium oxide is MgO. But I need to balance the equation to get the same number of magnesium atoms on each side and the same number of oxygen atoms on each side. Now, I can't mess with those small numbers. All I can do is put large numbers in front of each formula to try and balance it. So at the moment, I've got 1 magnesium on the left, 1 magnesium on the right, 2 oxygens on the left, 1 on the right. I can't simply put a small 2 here. I need to put the 2 here. So if I put a big 2 there, that means I've now got 2 oxygen atoms, but I've also got 2 magnesium. So I need to go back to this side and make sure I've got 2 magnesium atoms there. So let's check that's correct. 2 magnesium atoms, 2 magnesium, 2 oxygen and 2 oxygen. If you know you need more help on balancing equations, I've got a whole video dedicated just to balancing equations, and that's in my C1 playlist, Atomic Structure. We're now going to take a look at an idea called the conservation of mass. I'm going to react this piece of magnesium in this crucible with the oxygen that's around it. But before I do that, I'm going to weigh the magnesium, and I'll also weigh the magnesium oxide after the reaction. So I'm going to weigh this piece of magnesium, and we can see it weighs 0.18 grams. I'm also going to weigh the crucible and the lid whilst it's empty. The reason for that will become clear later. And the empty crucible and lid weighs 27.75 grams. I'm then going to put the magnesium inside the crucible and heat it up really strongly on the roaring blue flame of a Bunsen burner. And we'll come back to that in a few moments. We can now see the magnesium is starting to react with oxygen and it's glowing white inside the crucible. It's important I keep lifting the lid to allow more oxygen into the crucible to react with the magnesium. After it's finished reacting, we then let it cool and then place the crucible with the magnesium oxide inside and the lid onto the balance and take the new mass. And we can see now it's 27.97 grams. So after we'd heated up the magnesium and it had reacted with oxygen to make magnesium oxide, the crucible and the lid and the magnesium oxide inside weighed 27.97 grams. And we know that the crucible and lid weighed 27.75 grams. So if we take one away from the other, we know that the mass of magnesium oxide at the end was 0.22 grams. So the magnesium started out being 0.18 grams and it actually gained weight. It got heavier and it became 0.22 grams as it reacted with oxygen and joined with oxygen atoms from the air. So what's that got to do with conservation of mass? Well, conservation of mass states that the mass of the reactants on the left of the arrow is equal to the mass of the products on the right of the arrow. So we started off with 0.18 grams of magnesium. It changed into 0.22 grams of magnesium oxide. So the amount of oxygen from the air that must have reacted with the magnesium is 0.04 grams. Because then this side adds up to 0.22 grams and that side also adds up to 0.22 grams. So we can see the mass of reactants is equal to the mass of products. And that's what we mean by conservation of mass. We're now going to talk about how our understanding of atoms has changed throughout history. And this is something you need to know for your GCSE exam. So the first person to talk about atoms was Democritus, a Greek philosopher around 400 BC. So that's well over 2,000 years ago. And he used the word atom because it means indivisible. In other words, it can't be cut into any smaller pieces. So he thought that atoms were the smallest particle that all things were made of. Our understanding's moved on from that, obviously. We now know there's even smaller particles like protons, neutrons, and electrons. But he thought that atoms were solid spheres. In the early 1800s, John Dalton also agreed with Democritus that atoms are solid spheres. But he went a stage further and said that different elements had different types of atom. So if you had an element, you only had one type of atom, whether it's magnesium, that type of atom, or oxygen would be this type of atom. And that is still our definition of an element today. And that is that if you've got an element, you've only got one type of atom. He also said that compounds could be formed by joining different chemical elements together. Ideas about atoms had to change in 1897 when J.J. Thomson made a breakthrough. He discovered electrons, and he thought that atoms were a sphere of positive charge, so the whole atom was positively charged, and negative electrons were embedded throughout the atom like plums in a pudding. So he called this model the plum pudding model. The experiment that totally changed our ideas about atoms was Ernest Rutherford's gold foil experiment, carried out right here in Manchester. And he fired beams of alpha particles at some thin gold foil, and most of those alpha particles passed straight through the gold foil. But occasionally, a very small percentage of those alpha particles either deflected off course and went in another direction, or they reflected and bounced back from the direction they came from. These results led Rutherford to come up with his nuclear model of the atom. And here's two different ways of showing that model of the atom that you might see on your exam. Now, because most of those alpha particles passed straight through the gold foil, it made Rutherford believe that most of the atom is empty space. So we can see empty space here and lots of empty space here. And because a small percentage of those alpha particles were being deflected or reflected back, he thought they must be hitting something else that was positive, and he came up with the idea that all of the positive charge of the atom is concentrated down into a small central nucleus. So the main features are small central nucleus where all the positive charge is, lots of empty space, and then electrons on the outside of the atom. In 1913, the Danish scientist came up with the idea of electron shells, and he said that electrons orbit around the outside of the atom and they're on electron shells that are a fixed distance from the nucleus. So electrons either go around here or here, but not anywhere in between. The thing we haven't talked about yet is neutrons. They were discovered by James Chadwick. Our ideas about atoms haven't stopped there. There's even more complicated models of the atom that have been developed, and you'll learn about some of those if you continue to study chemistry at A-level. The second part of this topic is all about the different techniques we can use to separate mixtures, and I'm going to show you the first two of those techniques by using this rock salt. Rock salt comes from underground salt mines, so it's a mixture of the salt and also rock and sand. So we need to separate the rock and the sand from the salt. Many people think you can simply put this into a filter paper and it will separate out the salt and the sand. Well, let's see what happens if we do that. As you can see, both the salt and the sand have been left behind in the filter paper and nothing is passing through. And that's because we've missed out one very important step. Before I get onto that most important step, I'm going to crush the rock salt with a mortar and pestle to unlock any salt that might be inside big lumps of rock salt. And now comes the most important step that many people forget about. I'm going to add the ground up rock salt to a beaker of water so that the salt dissolves, but the sand and the rock will not dissolve because that's insoluble. And what I've done is I've used warm water so that it will help the salt to dissolve. Once the salt's had a few minutes to dissolve, then we can add the mixture to the filter paper in a filter funnel. And we'll come back to this in a few minutes when it's had a chance to filter. I've drawn a grain of sand to show the particles in it and also a grain of salt. And here we've got the filter paper showing how there's holes in the filter paper. Now when we try to do filtration without first dissolving the substance, we can see that the sand particles and the salt particles, because they're stuck together in those grains, they're too big to fit through the holes in the filter paper. But when we add water, the salt is soluble, and as it dissolves, the particles break apart into individual particles which are then small enough to fit through the holes in the filter paper. So what should go through the filter paper is salt and water, the salt solution. Whereas the sand is insoluble, that doesn't break apart, it stays together as one sand grain, and that is too big to fit through the holes in the filter paper. So let's see if that's actually happened. It looks like we've got some nice salt solution passing through the filter, and the substance that passes through the filter is called the filtrate, and left behind on the filter paper, which we call the residue, there we have the sand and the rock stuck on the filter paper. We still haven't got the salt from the salt solution. To obtain the salt, we then need to do a process called crystallization. The first stage of crystallization is to pour the salt solution into an evaporating dish and heat it up over a water bath using a Bunsen burner. We don't evaporate all of the water, we stop heating it up when crystals start to appear. This is then taken down and put somewhere for a few days, like on a windowsill, to let the rest of the water evaporate naturally, and then the final stage is to place it in an oven to dry the crystals. We've already seen how crystallization can be used to get the solutes back from a solution. That's the solid part, for example, the salt from a salt solution. But what if we wanted to get the water back from a salt solution, the actual solvent itself? Well, this is where we can use simple distillation. Inside this flask, I've got some copper sulfate solution, and you can see it bubbling away because it's been heated up by this electric heater. So the copper sulfate solution is being heated up here. It turns into water vapour, or steam in this case, and as that water vapour passes up here, it passes down this tube. This is called the condenser because we've constantly got cold water flowing around the outside of the condenser to keep that tube nice and cold. So as the water vapour comes through this condenser, it's going to cool down again and turn back into liquid water, and every now and then we see some water droplets dropping out here. So we're getting the solvent, the water, from the copper sulfate solution. So distillation is evaporation followed by condensation. This equipment I've set up here is for fractional distillation, and fractional distillation can be used to separate two different liquids so long as they've got different boiling points. So it's similar to simple distillation in that we've got the flask of the substances we want to separate that's being heated up, but then we've got this tall fractionating column. The fractionating column is usually filled with glass beads, or in this case, inside it's got some finger-like projections that stick into the interior of it. Then we've got a thermometer, and this is all connected to the condenser, which yet again is cooled down by some water flowing around the outside of it. So this could be used to separate a mixture of ethanol and water, because ethanol boils at 78 degrees, whereas water boils at 100 degrees. So what we would do is have the ethanol water mixture in the flask, turn on the electric heater down here, and both of those liquids would start to evaporate and pass up the fractionating column. When they hit the cold beads or the cold glass inside the column, they will condense and drip back down into the flask. So we've got this constant evaporation followed by condensation inside the fractionating column. The temperature on the thermometer would start to rise, but we don't start collecting any liquid here until we get to the boiling point of the first liquid. So when it reached 78 degrees, it would then steady off a bit the boiling point and we'd start collecting pure ethanol. When the temperature starts rising again, we'd stop collecting ethanol, and when it reaches 100 degrees on the thermometer, then we can start collecting the water, and we'd get water coming out of the condenser. The last separating technique I'm going to show you is chromatography. The first stage of chromatography is to draw a pencil line about 1 centimetre from the bottom of the chromatography paper. That's going to be our start line. It's important we draw it with pencil, not pen, because otherwise the pen would also dissolve in the solvent and start running up the paper and interfering with our results. We then put our sample colour on the start line. I'm using a green felt tip pen. The next stage is to suspend the chromatography paper in the beaker using a wooden splint and a paper clip. I've also put a very small amount of a solvent in the bottom of here, probably a couple of millimetres worth, and that's ethanol and water mixture. The important thing is the level of the solvent is below the level of the start line. As the solvent moves up the paper, it takes the dyes in this felt tip pen with it, and they will travel at different speeds. The dyes that are more soluble will travel faster and get higher up the paper. The dyes that are less soluble will travel slower and stay lower down on the chromatography paper. The solvent is moving up the paper, so we call that the mobile phase. The chromatography paper is stationary, so we call that the stationary phase. If the dyes are more attracted to the mobile phase, the solvent, they will move higher up the paper with the solvent. If they're more attracted to the stationary phase, which is the paper, they will get left further behind on the paper. You can see eventually my green pen separated out into all of these colours, and I'm going to show you how to work out the RF value for the yellow dye. So first of all, with the ruler I measured the distance from the start line to the middle of the yellow dye. I then measured the distance from the start line to where the solvent reached. To calculate the RF value, we use this simple formula. It's the distance moved by the dye divided by the distance moved by the solvent. So in my case, the yellow dye moved 3 centimetres up the paper. The solvent moved 4.1 centimetres. So 3 divided by 4.1 gives me an RF value of 0.73. Now that you've got the knowledge that you need for this topic, it's important you try out some practice exam questions, so head to my C1 playlist and look for the black and yellow thumbnails. Thank you for watching.